In lesson 10.6, we are going to take a look at probability, and specifically, we're going to take a look at geometric probability. So just a reminder at the top, it says that in probability, the set of all possible outcomes of an experiment is called the sample space. Any set of specific outcomes is called the event. That's usually what we're looking for to find the probability of. If every outcome in the sample space is equally likely, the theoretical probability of an event is given by the ratio of the number of outcomes in the event compared to the number of outcomes in the sample space. So the number of outcomes in the event is basically the number of ways it can occur compared to the total possibilities. For example, if we're rolling a die and we want to know the probability of getting an even number, the number of ways it can occur at the top would be 3. The total number of outcomes, the sample space, would be 6, because there's 6 possible numbers that could come up, for a probability of 1/2 or 1/2. Now, it says geometric probability is used when an experiment has an infinite number of outcomes. In geometric probability, the probability of an event is based on a ratio of geometric measures, such as length or area. The outcomes of an experiment may be points on a segment or in a plane figure. So if you take a look below, we're keeping in mind that with geometric probability, there's an infinite number of outcomes. So here is similar questions that you may see. We may be asked about the points on a line. For example, in this first one, our sample space is the segment AD. We know there are infinitely many points on that line. Our specific event, we may want to know what the probability is of getting point on segment BC here. Well, that's going to have to do with the length of the line. So we can say that our probability would compare the length of BC over the total length of AD. Where in the second figure and the third figure, we may be looking at probability of a point being in our shaded region. Well, we know that's going to have to do with the area. So we're going to do a lot of comparison today with the area of the shaded region compared to the area of the entire figure. Now down at the bottom, we say, or give the reminder that if an event has a probability P of occurring, the probability of the event not occurring is 1 minus P. And this would be because we know that our probabilities have to equal 100% or 1 total. So for example, if we know that there's a 40% chance that it's going to rain, there's a 60% chance it's not going to rain. And our probabilities can be expressed as percentages, as decimals, as fractions. A lot of time today, we are going to give our probability as a fraction, unless it says otherwise. So let's take a look at some examples. The first example, example A, we're going to take a look at points on the line segment. So it says a point is chosen randomly on segment PS. Find the probability of each event. Typically, I would say that kids usually find geometric probability to be a little bit easier than the other probabilities that they've taken a look at. Question 1, the point is on segment RS. Here, well, we know this has a length of 5. We need to know our total. Well, 7 plus 13 plus 5, well, this has a total length of 25. Our probability, 5 out of a total of 25. We always give our probability reduced in simplest form, so that would be a 1 out of 5. Question 2, the point is not on QR. If the point is not on QR, That means that it could be on PQ or RS. So there's a couple ways that I could do this. If it's not on PR, I could take 1 minus the probability of QR. Or I could take the probability of the PQ and the RS and add those together. Either way, we're going to find out that our probability is going to be 12 out of 25. Question 3, it says, what is the probability the point is on PQ or QR? So our keyword here, or, PQ or QR, it could be in any portion of this line segment. And so there, we can think about adding our two probabilities together. And in the end, 20 out of 25 would give us a probability of 4 out of 5. Let's take a look at example B. In example B, it says a stoplight has the following cycle: green for 25 seconds, yellow for 5 seconds, and red for 30 seconds. Question 1, what is the probability that the light will be yellow when you arrive? Now, although not required, I do think in a question like this, sometimes it's helpful to sketch a diagram or to sketch a picture. So if I were to sketch this, we could sketch this on a line segment and kind of map out the light cycle. If it's green for 25 seconds, let's see, 25 seconds for green, and 5 seconds for yellow, and then 30 seconds for red. Mine's going to look as so. What is the probability that the light will be yellow when you arrive? Well, we also need to know the total light cycle here. How long does this light run? Well, this runs for 60 seconds. Yellow, well, we can see that would be just a simple probability of 5 out of 60, but we are going to reduce, and so we're going to take 1 out of 12. Question 2, if you arrive at the light 50 times, predict about how many times you will have to stop and wait more than 10 seconds. We arrive at the light 50 times, predict how many times you'll have to stop at the light and wait more than 10 seconds. So first we need to know what that probability is. Waiting more than 10 seconds, that can be kind of tricky. We know that that would mean that the light would have to be red if we are waiting, but it said that we have to wait more than 10 seconds. So if I kind of think about this as my 30-second cycle here, and it about to turn green, in this portion, the last 10 seconds, if I arrive here, would you agree that I'm not going to wait more than 10 seconds? If I arrive in the last 10 seconds, I'm not going to have to wait. But if I arrive in this portion of the light cycle, I am going to have to wait more than 10 seconds. And I know since they have to add to 30, that that's going to be a 20-second time frame there. So in that 20-second time frame is when I have to wait more than my 10 seconds. Well, that 20 seconds out of the entire 60-second cycle is a probability of 1/3. So that's going to happen 1/3 of the time, actually kind of high. Well, how many times is that going to cause me to have to wait more than 10 seconds if I arrive about 50 times at the light? Well, we just simply need to know what 1/3 of 50 is. And when you multiply that out, you're going to get something like this. And since we are going to estimate about how many times that is, they did round that to the nearest whole number. So approximately it's going to be about 17 times. Okay, let's take a look at example C. Here we're going to use our spinner for our probability. Our spinner, though, is going to talk about the colors. So we actually need to do some labeling. This big section up here with the 140 is going to be our yellow, followed by blue for 52. 108 is going to be green, and 60 is going to be red. The degrees, what do the degree means? Well, this 140 means that that angle in there is 140 degrees. So, we want to know what is the probability that our spinner is going to land on yellow. We spin it one time, what is the probability? Well, the 140 degrees, describing our section of our circle, we know our total circle should add to 360. So, because they gave me the degree measures, finding the probability is actually pretty easy. 140 degrees out of the 360, we're simply going to reduce. Now, I know here, I can just reduce 14 out of 36. And 2 goes into both of them. That's a probability of 7 out of 18. What is the probability that if we spin our spinner, it will land on blue or red? So I could land on blue or I can land on red. Well, would you agree? I need to think about adding these two together. I can add or land on the 52 degrees out of the 360 or that other 60 degrees. And so when I add those together, I find out we get 112 out of 360, and it does reduce. As you reduce down, you're going to find that you actually get 14 out of 45. What is the probability that we would land not on green? Well, not on green means I could land red, yellow, or blue. So again, I could add those 3 up and take it out of 360. Or not on green, meaning I could just simply subtract out the probability of green. I know my probability has to equal 1, and I could subtract out the 108 over 360. In the end, after you've done some reducing, well, initially you find out you get 252 out of 360, which in the end is going to reduce to 7 times. Last one, what is the probability that our spinner will land on green and yellow? Well, I see green is 108, yellow is 140, but this is a probability of 1 spin. Are we going to land on green and yellow? No, we can't land on 2 colors at the same time, especially green and yellow. So this word plays a key role, and here this probability is going to be 0. It's not possible, right? We can't land on both colors at the same time. Now if we were spinning more than once, that would change a little bit, but this is on 1 spin. Last one. Taking a look at example D, we're going to find the probability that a point chosen randomly inside my rectangle is in its shape. They're asking me to round to the nearest hundredth. So in this case, I can see that we are going to give our probabilities as a decimal. I'm looking in question number 1 to find out what the probability that my point would be chosen to be in the trapezoid. So as I look at my diagram here, I can see my trapezoid in this entire space. Well, my rectangle is a 50 by 28. So the 50 by 28, the entire rectangle would be the sample space. And the outcome that we're looking for is my trapezoid. So I'm really taking a look at the trapezoid over the rectangle. Okay. My rectangle is a 50 by 28. My trapezoid, well, I can see that I have a base of 16 and 34 and height of 18. So I'm needing to compare that area. Now, it'd probably be easiest to figure these separately. If you take and find your area of your trapezoid, remember we're going to add these first, times by half, times by 18, you should find that you get an area of 450. And the area of my rectangle, 50 times 28, is actually 1,400. Now, if we were wanting to reduce these, we would actually find that it reduces to 9/28. But it does ask me to give a probability to the nearest hundredth. So we're going to take and just see what that's going to give me. To the nearest hundredth, I see it's about 0.32. So it's going to be about 32%. So this space in here takes up about 32% of that area. Question 2, what is the probability that we will pick a point in the square or the circle? Now, is it possible to pick a point in the square or the circle? Well, sure, one or the other, that can happen, but I see I have two squares here. So when I'm comparing my area, well, my square is a 10 by 10, so I know that this is 100 and this is 100. My circle here, pi r squared, well, my radius is 9. So when I'm taking a look at these probabilities, I could be in square number 1 or square number 2, or my circle, pi r squared, all of that compared to my rectangle, which we said had an area of 1,400. Now, I could simplify a little bit here. I could find now I'm just simply going to divide this out, but I am going to make sure that I put my numerator in parentheses. I want my 200 plus my 81 pi to be divided by my rectangle, 1,400. Now, I didn't mean for this to happen, but we actually are going to get a similar probability as above. That's about 32%. So, again, to the nearest hundredth, this is going to come out as about 0.32. Now, if this question would have been stated a little differently and wanted to know the probability of the square and the circle, what would we say? Well, the square and the circle would be a probability of 0, right? You can't have 1 point in both of those regions. Can I have the probability of being in the circle and the trapezoid? Yeah, the circle and the trapezoid would have to be in this region here, but that would fall because the circle is inside the trapezoid. So our reading is going to be important here today. As I said, I want you to find your probabilities as a fraction unless they state otherwise. If you have further questions on this, please stop in and see me.